Hi, it's Milasoft. In today's video, I'm going to discuss character sets. What you see on the screen is the normal ROM character set of the Commodore 64. This is character 0, character 1, 2, 3, 4. It goes from 0 to 31, and then line 2 is 32 to 63. Line 3 is 64, and so forth. The reason I've chosen to display the character set using Ultrafont, which is a Compute Gazette character set editor, is because it perfectly shows you the different banks of memory. For example, this would be, in Ultrafont, this is at 7,000, this is at 7,100, 7,200, 73, 74, 75, 76, and 77. So a complete character set on the Commodore 64, the full font, will take up, say you have a character set at 2,000, a full character set will be from 2000 to 27FF. You're looking at 800 bytes. So 2048. You get 2048. I don't know if we can do math on here or not. We can. 2048 divided by 8 gives you 256. There are 256 characters on the screen here available to you, made up of 8 values, 8 bytes each. I'm not going to get into the technical aspects of it because I find that if you're trying to learn machine code, it just further confuses you. There's a lot of articles already available to explain how character sets work and banking. So I'm just going to say that on this Commodore 64, you can have 4 banks. Bank 0 is from 0 to 3FFF. Bank 1 is from 3FFF to 7FFF. 2 is from 8,000 to BFFF. And bank 3 is from C1000 to FFFF. So take your 64 and think of it like a huge filing cabinet. You have a filing cabinet with 64 drawers in it. And the computer has very small arms. It can only reach a certain number of drawers every given time. So we have to separate everything into banks. There are 4 banks, which you can think of as sections to the filing cabinet. The bank that we currently use is bank 0. And for the purposes of this video, I'm going to stick with bank 0. You can, however, switch banks. You don't have to stay with 0. So if you load up a machine language game, something that's pretty advanced, like maybe R-Type or Catechus, I don't know how to pronounce it, you might find that the character set is in a different bank, one of these perhaps, and the screen memory is also in a different location. I've seen games with the character set up at C1000. I've seen games with the screen memory at C1000. Screen memory normally is at 0400, which is 1024 in decimal. Who hasn't typed poke 1024 with a value? I think we've all done that. So just to reiterate, the 64 has 64 drawers, like a filing cabinet. This is an analogy because analogies help you learn. And each of those drawers is made up of different banks. So this would be 16 drawers, 32, 48, a total of 64 drawers. And it can only use one bank at a time. It can only see one bank at a time. The VIC chip, when it draws the screen, it can only access one of these at a time. We could, of course, relocate to any one of these banks if we want. Why you would want to do so, I'm really not sure why people do that. I guess it's easier if you have your code down at 0800. I don't know why people choose to relocate character sets. It can be done, and that is known as bank switching. You've probably heard of bank switching before. It's not when you decide that you're tired of your current financial institution. It means you just want to switch out to a different bank using location DD00. And you can have your screen, like I say, at C1000, or you can have a character set up high. You can just switch things around. All you need to know is that when you turn your 64 on, it is defaulting to bank 0, which is from 0 to 3FFF. Keeping that in mind, that also means that we have different options for character sets. Character set is, of course, what you see here. I'm going to load in a custom character set into 7000 memory. 7000 just happens to be where Ultrafont puts the character set. And as you see, the character set has now changed. It's a custom character set. It looks different from the original ROM set. And it makes games appear a little bit more polished. A game that has the default ROM set doesn't look very professional. It looks like, it was written in BASIC. So this is just a way of making your game stand out. What a lot of people do, Pac-Man is one of the games. They will use the first two rows, the first two banks, as the letters and numbers, and then everything from here on down is for the game graphics, like the Pac-Man or the dots or the maze characters, because you really are only displaying words and numbers on the screen. In a game, the rest of it is either maze data or ships, what have you. So in this video, I'm going to be focusing just on the first two. I call them banks. You can call them rows, what have you. So if your character set was loaded in to memory, as I say, at 7000, this would be 7000 here. This would be 7100, 72. And just to put that to the test, I'm going to go into the machine language monitor, and I'm going to fill 7100 to 7108 with FF. And you now notice that the space is a solid block. So we've replaced the space character with a solid character. If I was to fill 7000 to 7008 with FF, then the first character becomes a solid block. 7000 is not an ordinary place to put a character set. If we're using bank 0, which we will be doing, it will be in a different area of memory. These are a list of the pokes that control location D018. You've surely used 53272, 21 for uppercase, 53272, 23 for lowercase, but we also have these four values. We can put a character set at 2000, 2800, 3000, 3800. We can even put one at 0800, which would be 53272, 18. So you may want to write these down. I would recommend that you do if you plan to use custom character sets. I'm going to load in my custom character set into 2000. This is done using the machine language monitor. Poke 53272, 24. We now have the custom character set. Hi there. The VIC chip, when it draws the screen, is now looking at location D018 to get the character set information from. It's pulling it from 2000. If I poke 53272, 29, nothing shows up because I don't have anything at 3000. I can load a character set into 3000 and then suddenly I have character data. Please make note of this. 21 and 23 are for the normal upper lowercase. You might be asking yourself, what do 21 and 23 point to? They actually point to 1000, but it's invisible. I say it's invisible because the character ROM at 1000 is something that we don't see. If we look at 1000, it's usable to us. It's character RAM. We can put stuff at 1000. I can fill 1000 to 2000 with 0. And of course, the character ROM doesn't disappear because it's in ROM. So I don't mean to confuse you. Just keep in mind that the default character set you see when you turn on the 64 is invisible. It's at 1000. If you want to use a custom character set, you can put it at 0800, 2000, 28, 3000, or 3800 for this particular bank, which is bank 0. And that will provide you 256 characters to use at your discretion. If you watch my last video pertaining to how to do a smooth scroll, we're going to be recycling that same code. At the bottom of my code, I'm going to be loading in character set 2. That is the name of the file. I will include it on the disk that will be supplied in the description for the video. And we're going to load it at 2800 in memory. It's a binary file, so we put !binary. Name of the file is cset2. That's the name of this particular character set. We put comma 2 because the file begins with 2 bytes, 00 and 28, because when you load it 8, 1, the first 2 bytes say the file has to load into 2800. Because we're forcing it into 2800, we don't want those 2 bytes there. Otherwise, the first 2 bytes would be 0 and 28, and all of the character set would be off by 2 values. So we include the character set at 2800. And then what we do is we go down and we just add this line. Load 27, store in D018. Because 27, it will be 26. 27 will work because the last bit, being a 1, is ignored. So now when the raster is drawn on the screen, think of it like a man on a scaffold painting the screen. That's the raster line. He starts at the top, and he works from the left to the right, and he moves down to the next line, left to the right, and he paints the screen different colors, which is how we get raster bars, but he also controls the default character set. I just want to make sure that this is configured properly. I'm going to execute the code by pressing Control F5. You can also go to Build and click Build and Run. Source code will be included as well. And now the smooth scroller is no longer the old character ROM. This looks more polished, looks more fancy, more professional, looks kind of like a demo should. As it draws the screen, as the little raster bar makes its way down the screen, we've already told it to fetch the character information from 2800 because of location D018. If I set it back to 21, I can't do it because it's doing it in the interrupt. But if I search for where it's storing it into D018. If I change this to a 15, that gets put into D018. 15 is 21, the uppercase. You see it switched back to uppercase. So again, just make note, location D018 specifies where to fetch the character set from. I'm going to go back into the source code, and I'm going to switch it up to character set 3. Character set 3 is a little bit different. I told you that we would get into 2x1 scrolls. Now you can see we have basically half of a character set. Poke 53272, 26. So I will write Milasoft was here. And then if I go into reverse mode and I type Milasoft was here, you can see there's a 2x1 font. And if I poke 5327221, this is all that we're doing. We're printing normal text, and then we're printing it in reverse. And because of the way the character set is made, we get a 2x1 font. I'm going to load the Ultra font back in, and I'm just going to show you how that looks. We have a redefined character set with A to Z and numbers, and then down where the characters would be in reverse, we have the lower half. Now, in order to correct this problem, I'm going to scroll through, and this is where it places the text on the screen on the far right for the smooth scroll. If you watch the other video, and I recommend that you do, we take 0609 and we store it in 0608. And that does this. Give me just a moment. So this is 0608. This is 0609. And all we're doing is we're saying load 0609, store in 0608. So the B moves there. We use X as the offset. So every time we increment X, it adds 1 to these values. So what it will do when X is incremented, it will take the C and move it to the left one, the D to the left one, E to the left, and so forth. So I'm adding 2 lines of code, which are just saying take 0609 plus 40 and store at 0608 plus 40. I could do the actual math and put what the true values are. That would be 1, 2, 3, 4, 0630. So let's do it proper. 0631, comma X, store in 0630, comma X. That's going to cause 2 rows of data to move from right to left. And then when we put the top half of the character on the screen at 0608 plus 39, we're using plus 39 because we want it to appear 39 characters over on the right side of the screen. We're going to do a clear carry because we want to do some addition and we want to remove anything that might be in the carry register and add number string 80, which will put it into reverse. And we're going to store that at 0630 plus 39. So 0608 is the first line, 0630 is the second line, and we're just taking the first byte and putting it in reverse field. If this works, and it should, we'll have a 2x1 scroll. There we are. There is our 2x1 scroll. The top half of the screen, of course, is not done properly. We have to put it into reverse mode. Welcome to my new... You get the idea. That's a 2x1 scroll. That will be included in the disk image. Feel free to play around with it. So that's going to cover character sets. It's really pretty straightforward. Just remember these pokes, and there are plenty of character sets available online to download. I will include a random sampling of character sets, and you will just include them at either 0800, 2000, 2800, 3000, or 3800. And then you will want to include right here. You can actually put it, you can take this out. We don't need it in the IRQ. We can put it right here. So it fires up when we're initializing the screen. We don't need to do it within the interrupt. It's already been set. And that gives you more time to do things with your interrupt. There's nothing loaded into the character set. You're not limited to just characters. You can also clear out the information, and you can create logos or graphics for your own game. I'll turn on the joystick, and you can create, you can create a maze, you can create a logo. Ultrafont does support multicolor characters. We can get into that in a different video. This is just a single color character. As an example, we can erase the @ sign, and we can create a little Pac-Man fellow. Kind of, sort of a Pac-Man fellow. A very poor looking one at that. And then within your game, you can have this Pac-Man character. I press T. T is for test mode in Ultrafont. L is for load. S is for save. You can play around with the function keys. Ultrafont is free, so I can include that on the disk. It was published by Computes Gazette, as I mentioned. And we should also get into the bits. The bits are important. This is where you're going to need to understand how bits work. So the bits go 128, 64, 32, 16, 8, 4, 2, 1. How are characters stored in memory? So every character takes up 8 bytes. 8. And the way that works is because it's an 8x8 grid. So every memory location is one line across. This would be 7,000, 7,001, 2, 3, 4, 5, 6, 7. And that would be 7,008. As an example, if I fill 7,008 with 255, the top of the A is now solid. Every byte is one line across of the character set. So this is the A, B, C, D, E, F, G, and so forth. Whether your character set is at 2,000, 3,000, it doesn't matter. Every line, when you look at it in the monitor, is a character. The number itself represents the bits. Just as an example, I'm going to fill in from left to right, like this. Try to get it right the first time. And then if I go into memory and I look at 7,000, we have a value of 128, 64, this is in hex, of course, 32, 16, 8, 4, 2, 1, just like here. because we've turned on those bits. 128 plus 1 is 129. So if I was to clear out the character and turn on the first and the last, we'll get rid of A. If I look at 7,000 now, it has an 81 hex, which is 129, because those two bits are turned on. If I turn on the last two, or rather the first two, 2 and 1 equals 3, we should have a value of 3. If I change that to a 7, then it will turn on 4, 2, and 1. That is how a single byte controls which of these individual boxes gets turned on. That should make sense. I hope that makes sense. When I fill 7,000 to 7,008 with FF, FF is 255. That is all of these numbers added up together. Therefore, we get a solid block. So I'm going to leave it at that, and I'm going to now dive into Sprites. Sprites is going to be a little bit more comprehensive when it comes to the bits, so stay tuned. I've decided to include a little bonus at the end of this video with regards to ripping out graphics from games. Let's say that you find a font that looks very appealing to you, and you'd like to use it in your own work. Or maybe you find some graphics that you'd like to include in your own work as well. I have the game Rambo up and running. I'm going to reset, doing a soft reset. If you had a reset button on your 64, you would use that. If you had a cartridge, you could do a reset through that. But you're not doing a full system reset. You're just doing a soft reset, so the information is still in memory. I'm going to load a character set ripper by the group Alpha Flight. You load it 8, 1. It loads into very low memory. And then by using the function keys, it allows you to page through memory until you find the graphics that you're looking for. In this case, we can see the 2x2 font. There's probably game graphics in here as well, if we dig deep enough. Now that we have the font up on the screen, you press S to save. How many blocks? I would imagine we would put 8. And then it's going to ask for a file name. I will call it font. I'm going to wait for the disk to finish. Then I'm going to do a hard reset. And I'm going to examine the disk and see what is on it. Okay, I see the font file is there. I will load it 8, 1. It ends, so it loaded at 0800. I know that because I've checked 2D and 2E, which tells me the end address is 1000. So the font has loaded at 0800. Referring to the content in the video, we know it's POK 53272, 18. Doesn't look quite right. I'm going to attempt to fix that by moving BASIC up to 5000 and then load font 8, 1. POK 53272, 18. That's better. What happened is, because BASIC was at 0800 and I was loading the font 8, 1, it thought it was a BASIC file and it changed BASIC. So you have to either load it from a machine language monitor, or what I did, I moved BASIC up poke 44, 80, just an example, which moves BASIC into 5000. And you have a new font that you can use. If you're going to use it, I would recommend crediting the person who created the font. The Ripper disk is actually a really cool program. You can also use it to rip out sprites, and we're going to be getting into sprites in the next part of the video. In this part of the video, we're going to cover sprites. Now, if you've used sprites in BASIC, this should be easy for you to understand. It's not very complex. In fact, it's quite easy. The only challenge is that there are a lot of memory locations to remember. The first location is D015. D015 is how many sprites you would like on the screen. And it uses the bit system. So if you want 3 sprites, would you poke 53269, 3? If you want 3 of them, let's try it. We only have 2 sprites showing. That is because we use the bit system, where they're numbered 1, 2, 4, 8, 16, 32, 64, 128. So if you want 3 sprites, you must add 1, 2, and 4 for 7. If you want just the very last sprite, then it would be 128, 64. It's just a matter of which sprites you would like to enable. If you want the first, second, and last, then that would be 131. Let's say that we want 255. We want all of the sprites to be on. So that is the D015. That's about the easiest register that there is to understand when it comes to sprites. Just get a piece of paper and write down the bits, and then add up which sprites you would like to have on. The next register, D017, 53271, is the expansion for Y. And it works on the same principle, where you tell it which bits you would like to expand. So 128 will expand the final sprite. 129 will do the first and last. Generally, you would want this off. You don't really want to expand your sprites unless necessary. It makes them look blocky. The next location is D01D. D17. And that would be the X expansion. I will put a little image up on the screen. 53277, 2. It expands the second sprite. 128, it expands the very last one. If we put 3, it will do the first and second. And generally, we will want that to be a 0 as well. So we have the number of sprites, the X and Y, which you probably want to be set to 0, and they use the bit system. Next comes the color. The next registers are D027 to D02E, and those are quite easy. It's just the sprite color. So 53287, 1, that's white, black, 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 and so forth. I don't imagine that you'll be making too many single color sprites. Generally, we like to use multicolor sprites. The next register is D01C, which is 53276, and it is the sprite multicolor register. The way that works is you select which sprites you would like to be multicolor, and you put it into D01C. So if we just want the last one to be multicolor, we put 128 into D01C. The colors for the multicolor are done using 53285 and 53286. And then the third color is again defined using D027 to D02E. So 53293, I believe. No, 53294. It's not really the goal of this video to teach you how to do multicolor sprites. I just want to show you how to use sprites and animate them in machine language. So I will leave that to you to figure out how to actually design them. But 53276 is for the multicolor register, where you decide which ones to turn on. Now for the fun stuff. Every sprite has a pointer. When the raster beam, also known as the man on a scaffold, paints the screen, he needs to know, just like we need to know where the character set is, we need to know where the sprite data is. And in bank 0 on the 64, that is at the very end of screen memory. So screen memory starts at 0400. The sprite pointers are at 7F8, which is 2040. So 7F8 to 7FF, I believe, just before BASIC kicks in at 0800. Those are your pointers. And to understand the pointers, it's actually quite simple. You take where you want to put the information. Let's say we want to have sprites at 2000. What you do is you take the value 8192, which is decimal, divide by 64, and you get 128. You're always going to take the area of memory you want to put the sprites in, divide by, wouldn't be a Milasoft video without a couple of typos, divide by 64, and then that goes into the pointer. So I'm going to poke 2040, comma 128, 2041, and you should see them starting to change. And if we, the first color is, I would imagine, blue, which is why we don't see it. Yeah. If we go into memory using the monitor and look at 2000, it's full of FFs, which would make it a solid block. Just to demonstrate, I will change some of these values up, and that alters the very top of the sprite. Sprites are 24 pixels wide by 21 high. So they go roughly 3 characters across, in fact, exactly 3 characters across, and then 21 pixels high. When it comes to moving the sprites on the screen, we use D1000, D1001 for the first sprite, and we just continue to go up from those values. So D1002, D1003 is sprite 2, X and Y, and it continues for 8 sprites. So it goes D1000, D1001, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, D1000E, D1000F for the very last sprite. To demonstrate, if I go in to D1000E and I change the Y value to an A2, it's now moved down just 2 more pixels. So just to recap, we're taking a look at these values 1, 2, 4, 8, 16, 32, 64, 128. We're adding up the ones we want to use for sprites, and we put it in D015. We're doing the same for the X and Y expansion, which if you want a nice looking sprite, we usually leave those off. If you want a single color sprite, then we will use DO27, 28, 29, 2A, B, C, D, E, which is at 53287 and upwards for the single color of the sprite. Most sprites in games are going to be multicolor, which is DO1C, and that again uses the same bit system where we decide which ones. So most likely it's going to be 255 so that you have all of the sprites enabled as multicolor. As far as defining the multicolor, there are 3 locations. You use the initial color, so 53287, and then you use 53285 and 53286. Those are the secondary colors. I will put that up on the screen. Again, it's not the focus of this video to teach you how to make a multicolor sprite, just how to initialize them. And then we're looking at D1000, D1001 for the X and Y of the first sprite, D1002, and this is where we're going to get into the fun stuff, which is actually animating them and moving them around, etc. So for this, we're going to go into C64 Studio because I think that is the best environment to create machine code. So let's get right into this. With C64 Studio in memory, we're going to go to File, New, Assembly File, because we are going to be programming in machine language. The first line of code indicates where we would like to put the program. For today, let's put it up at 49152, which is going to be C1000. And let's get right into it. Load A with 93, hex, JSR FFD2. If you've watched my previous videos, and I hope that you have, FFD2 takes what is in the A register, currently at 93, and prints whatever is in A. So it's going to load A with 93, go to FFD2, which is a kernel routine that says, hey, what have you got in A? Let me print it to the default device, which is the screen. And these 3 lines of code will just clear the screen. Quite boring, but let's see it in action. SYS 49152, it has cleared the screen. We now want to set up the sprites. For our example, let's use 255 sprites. So we're turning on all of the bits. 120, where you're turning on all of the bits, 1, 2, 4, 8, 16, 32, 64, 128. Store D015. How many sprites are showing? Load A with 0. Store in, we're going to load A with 0 and store in D017 and D01D, which is going to be 53271, the X expansion, and DO1D, which is the Y expansion. Now we want to find a place to put our sprite data. Let's choose a safe area of memory, which will be 832. 832 is around the cassette buffer. If we divide 832 by 64, we get a low number of 13. 832 is going to be in 340. We now need to set up the sprite pointer. We're going to use 0D, which is 13, and we're going to load X with 0. And rather than set up every sprite individually, I'm going to store in 07F8, comma x, increment x, compare x till it reaches 8, branch not equal loop. And what this does is it sets up a loop where a is equal to 13, 0d, x is set to 0, it puts 0d in 7F8, and it increments x till it reaches 8. So it's putting d into 7F8 and then incrementing 8 times. The result will be this. It should be setting up the sprite pointer for all 8 sprites. And if we examine memory at 7F8, it has done just that. 7F8, just to remind you, is the sprite pointer that tells the VIC chip where the information is for the sprites. And that is going to be, we take a value and divide it by 64. We are putting our sprite data at 832. 832 is below basic. It is in location 340. It's safe, so basic's not going to overwrite it. And I'm just going to temporarily, actually let's do this in machine code. Now that we have defined our sprite pointer, I'll just go over that again. So 7F8 to 7FF are the sprite pointers, and that is a value that you multiply by 64 to tell the computer where to fetch the sprite information. As an example, if we have sprite information at 2000, which would be 8192, we would divide 8192 by 64, and that would be our sprite pointer. Since I want to use 832 to hold the sprite information, I'm going to be putting a 13 in 7F8. 832, of course, is 340. So let me just show you. I will turn one sprite on. I will set the Y and the X, and I will poke 2040, comma 13. And then there's nothing there. If I poke 832, comma 2, we see a single pixel. 833, 834, 835, and that is how that works. So we are saying fetch our sprite information from 340 hex, also known as 832. Now let's put some information in the sprite, because as you saw, the sprites were empty. We will load A with FF, we'll load X with 0, store A at 0340, comma X, increment X, compare X to 63, branch not equal loop 2, there, we have a full sprite. Okay, now let's get into the X and Y coordinates. We've set up the number of sprites we want. We've turned off X and Y. We've set the sprite pointer. We've filled the sprite memory, which is 340. We should do color. We'll load X with 0. We'll load A with 7. store D027, comma x, increment x, compare x with 8, branch not equal loop 3. I could, of course, combine this code because I'm doing this 8 times and this 8 times. I could put this code up in here just to save time. And now all of the sprites should be in yellow, D027 being the first sprite color register. There, perfect. Set up sprite Y position. We're going to put all of the sprites on the same Y position. Let's pick a value of A0, load X with 0, store A at D000, comma X. Now we have a bit of an issue here, and the issue is we cannot go increment X because it will go to D1001, which is the first issue is it should be D1001. D1000 is the first sprite X position, D1001 is the first sprite's Y position. And if we put A0 in D1001, that's okay. But if we increment X, it's going to go D1002, which ends up being the X position. We don't want that. The solution is we need to increment X, and then compare X to 16. I will explain why in a moment. All right, so if this is our layout, D1002 is the next X, D1003 is Y, D1004 X. This is how they're laid out in memory. It goes XY, XY, XY for every sprite. And we just want to do Y for now. So I'm putting A0 in D1001, which sets the first sprite Y position. Not an issue. But if I increment X, this is the X position. We don't want that. We want the next Y. So we have to increment X twice. So X is 0, 1, 2, 3, 4, and actually, I'm sorry, my mistake. D1001, D1003, D1005, it takes every other byte and then checks if it's 16 instead of 8. Syntax error. Get rid of this. Now we just have to define the X positions. So to do that, I think I'm going to use an array, X position, byte. I'm just going to guess what they should be. 3, 30, and now we're going to make another loop. We're going to load X with 0. We're going to load A with X position, comma X. And we're going to store in D1000. Again, we run into the same issue. We cannot use comma X because, again, D1000, D1001, D1002, D1003, what's going to happen is it's going to take the first X position, which is 30, and put it here. That's exactly what we want. But when we increment x to go to the next one, it's going to store at d1000, x, which will put it here. We don't want it there. We don't want it. We want it at d1000 too. The solution is to introduce another variable. Holy shit, man. And store at d1000, y. Then we will increment x, increment y, compare x with 8, branch not equal loop 5. So I'm going to walk you through how this works. It sets x and y to 0. It takes x position, x, which is 30, stores it in d1000, y is 0. So that sets up our first sprite. Perfect. Increment x, so x becomes 1. Has x reached 8? No, go back up. Load x position, 1, so it takes 50. And rather than storing it in d1001, which we do not want, it puts it in d1000, y. We've incremented y twice. So it goes from 0 to 2. So it goes d1000, d1001, d1002, and puts it in the right position. It's just playing hopscotch. And if this works on the first try, we should have a screen with 8 sprites. 1, 2, 3, 4, 5, 6, 7. I know what's happening. All right, and this gets us into the next part of the video, which is the limitations of sprites. So we have 1, 2, 3, 4, 5, 6, 7, 8 sprites. The Commodore 64, of course, is an 8-bit machine. The highest value you can have in memory is 255. We cannot put 256. It just doesn't work. There are 40 characters across the screen, and each character is made up of 8 pixels. That gives us 320 x pixels. There are 25 lines. Each one, of course, is made up of 8 pixels. That gives us 200 y pixels. The screen is 320 by 200 pixels. Because the Commodore 64 only allows a maximum of 255 in a memory location, we run into an issue trying to set the x position of sprites. Y is not an issue. We can easily change that. I can easily go 53249, 244, and it moves the y position. That's not the issue. The issue is we can only go so far before we hit 255. So allow me to demonstrate. Poke 53249, 160. Poke 53248, 255. This is as far to the right as we can get. We cannot go here because it wraps around to 0. We have 0, 255. What do we do? 10. D010 is known as the most significant bit, and it utilizes D010 is known as the most significant bit. This is where D010 comes into play. It is known as the most significant bit. So we have each individual X and Y location, and then we have D010. And what D010 does is it adds an extra 255 to the X position. It allows the sprite to go over into the right-hand side. So for now, let's just use one sprite. We'll poke 53248, comma 20. So x is 20, y is 160 currently. And I'm going to poke 53264, comma 1, which is going to enable MSB for the first sprite. It is now moved over here. But the value of the sprite is still 20. The x position has not changed. It's still a 20. 21, 22, and if I turn 53264 off, it goes back here. If we were to use an analogy, I would say maybe that there are two screens, two mirrors, whatever works for you. Just think of an invisible line right about here, and 53264, also known as D010, flips the sprite over into this half of the screen if the bit is set to 1. So if we have D010, if it's all FF, that means every single sprite is going to be on the flip side. So if we want to move a sprite from left to right, we'll start from the left side with D010 being 0, of course. And I would go for I equals 1 to 255. That's as far as it will go. But then what we can do is we can poke 53264, comma 1 to turn on the flip side and go for I equals 1 to approximately 40. Poke 53248, comma I colon next. Let's go a little bit further. Oops, okay, I forgot to turn it off. Now the sprite moves flawlessly across the screen. In machine language, we have to do the same thing. I'm just going to go over it again because I don't want to lose anyone. We have location D1000. This is the X position for the sprites, and then the Y position for the sprites. This is for the first 4 sprites. So X, Y, X, Y, X, Y, X, Y, and then D010 controls all of those sprites. For the flip side, I know it's not called the flip side, but I want you to understand it. It's MSB, most significant bit. So it changes the bit. It just flips it over so it can be greater than 255. When it comes to moving sprites across the screen, that's where we get into the challenge. Let's do a little bit of code here. Let's go load A with X position. So it's just going to take the first value, 30, store D1000. So that's the first sprite X position. In fact, we can take this out. We're just going to work with one sprite for now. And then we're going to increment D1000. So it's going to increment the X register. And then I'm going to insert a delay in the form of waiting for a key press. Just to slow it down. I don't want it to be super fast. Eventually we'll replace this with a better routine, but for now. So here is how it's going to work. We're setting up the first sprite X position to be 30. We're going to increment that position. We're going to wait for a key If it's equal to nothing, go back up and wait, and then go back up to loop 5 and increment it again. And I will demonstrate to you what happens. It moves slowly across the screen as it increments the X position. And then when it reaches the far right, watch what it does. It reappears on the left. Why does it do that? Do you have any theories? Because we are using the increment command. So when it reaches FF 255, which it is right now, and I press a key, it wraps around to 0. So it goes FD, FE, FF, and it cannot go higher than FF because that's 255. That's the maximum value we can have in any register, so it wraps around to 0. And this is where we're going to get into using the MSB. Let's load A with 0 and store it into a label called MSB. That's going to tell us when the sprite is on the flip side. We're going to also put 0 in D010, which is the MSB register itself, to ensure that no sprites are on the flip side. And then we're going to increment D1000. Actually, before we increment D1000, we're going to load D1000, compare it with 0. If it's not equal to 0, go down to plus, where plus is going to increment D1000. And I feel I might be losing a few of you, so let me just reiterate what we're doing. We're setting X for the first sprite to 30. We are then putting 0 in a variable called MSB, which is going to be a flag. I believe they call it a flag because it works like a racetrack flag. It's just a visual indicator. It's to say, hey, something has happened. We're going to ensure the sprite is not on the flip side. It's over here. We're going to load the X register and check to see if it's 0, which it is currently not. So because it's not equal, it goes down here and increments it. So it will move over and over and over and over. And when it hits 255, we know it wraps around back to 0. So right here is going to be where it has wrapped. We are then going to load MSB, and we're going to compare to 0. Branch not equal. Temporarily, we're just going to skip. So it's already been set to 1. Just skip. And then we're going to load 1. We're going to put it in MSB to indicate that it is wrapped around. And we're going to load 1 and store it in D010. And then we're going to test that code. I'm not sure if it's going to be flawless or not. A little bit of a flicker, but it did go from left to right. I'm going to introduce a little bit of a delay. So I'm going to load X with 0, load Y with 0, increment X, branch not equal, we'll call it A1. So that's going to cause X to increment in a loop. That's going to cause X to increment in a loop. And then we're going to check Y till it reaches 8. And that should slow things down a little bit. In order to reduce some of the flicker, I'm going to introduce a raster line check. So it's going to load DO12, compare it to 30, which is about the top of the screen, and then wait, so that it's not refreshing the sprite as it's drawing it. That is a little better. It's still quite fast though. So I'm going to introduce a small delay. We have nice smooth animation, and it still flickers a little bit. I think what we should do is turn off all of the other sprites and just have one sprite enabled. And the flickering has stopped. I realize now why it's flickering, because we're setting DO10 to 1, putting the sprite on the flip side, but then we're incrementing it so it's shifting from 0 to 1 immediately. So we will just have it jump over that first increment. And this time, let's hope it is flawless. Perfect. Perfect horizontal movement. I've decided to update the code because the sprite was flickering a little bit and it wasn't ideal. So this is the next generation code. We're clearing the screen and calling FFD2. We're still putting FF in DO15 to make sure all 8 sprites are enabled. We're turning off the X and Y expansion. Sprite pointers are still at 340 hex. We're setting 340 with a solid block, 255, so it's making a solid block for a sprite. The sprite colors are set to yellow. The Y position is still A0. And of course, we have the X position. Here are the new changes. So I'm waiting for the raster beam to hit F0 right about here on the screen before we do any changes, because if we move the sprite while the raster line is on it, it can cause what's known as tearing, where the sprite looks like it's torn in two. And now I'm loading X with 0. I'm loading D1000, X. I'm doing a clear carry, which is like taking a chalkboard and erasing the chalkboard when you want to do math. You know, when you carry numbers while you're doing addition, CLC just clears the carry. It sets it. It's like clearing your chalkboard, so you can add 2 numbers. And then we add 1 to D1000. And then we're transferring X to A. And then we're multiplying by 2, doing an LSR. We transfer A to Y. And then we load a table. I now have a table which has all of the values that we have to put into D010 to put the sprite into the flip zone. And this, of course, this is just the bits, 1, 2, 4, 8, 16, 32, 64, 128. And when we run the code, we end up with all of the sprites moving seamlessly to the right-hand side of the screen. I can go into the monitor and change the Y positions. We can do it in the code as well, but I just want to do it while it's running to show you how it looks. Now we have kind of a star field, I guess you could call it. And again, the way that works is we wait for the raster beam to hit F0 at the bottom. Are you equal to F0? No, go back up and wait. We want to wait for the man who's painting the screen to be at the bottom before we make changes. We load X with 0. We load D1000, which is the X position. We add 1 to it, and we store it. And we do a branch carry clear. So if it's not equal, if it hasn't wrapped around back to 0, it goes to the next sprite. If it has wrapped around to 0, then the carry flag is set. It ends up being what we call BCS. So we transfer X to A, we multiply by 2, we put that into the Y register so we can fetch the proper MSB value for that sprite. And then we do an exclusive OR to toggle it. So if it's in the flip zone, we take it out of the flip zone. If it's not in the flip zone, we put it in. Exclusive OR will toggle the value, and we store it in D010. A little bit more complex than I wanted to get into, but inevitably, that is how we do sprites in machine language. I would like to have all of the sprites on a different Y position. So what I will do is, let me see, I'll just make a new table, call it Y position, and let's just pick some arbitrary numbers here. 1, 2, 3, 4, 5, 6, 7, 8. And we will load, take all of this out. Load Y position, comma X. Store D1001, comma X. Just for fun, let's increment D001, comma X, which will increment the Y position. So they should now move in a down right position. So that should get you underway as far as creating sprites. Do you see how it's tearing right there? How the sprites look a little bit torn? That's because the raster beam is updating when the sprite is on that line. So I hope that this gives you some insight into how to get your sprites moving, how to get them onto the flip side, so to speak, using D010. And in our next video, let's try to put everything together and make some sort of a game where we can move a sprite around with a joystick. This is Milasoft saying thank you for watching, and we'll see you in the next video. Source code will be provided in the video description.